All right, guys, here I want to talk a little bit about perception. Um, I've been hitting very hard about what's happening in your body. What's happening in your body is sensation. But of course, once that information gets to your brain has to figure out what it is. So that is called perception. And one of the first concepts I want to talk about is the difference between top down processing versus bottom up processing. Sometimes you see something and you know what it is. Your brain already knows what it is. And so before your eyes send the information to your brain already made the picture. Um, if you know that sitting next to you, maybe you're on the couch and right next to you on the couch is a fan, okay? Even though you're not looking at the fan, you know the fan is there. You could imagine the fan. And if you turned to look at the fan and the fan was gone, you would be surprised. It would, even if you weren't looking for the fan, if you turned and the fan was gone, it would sort of make you feel weird. This is because your brain paints a picture first. It gets the signal from the brain, from the eyes, and then it paints the whole picture, the whole world you live in inside your head. And then it will um, double check with the eyes to make sure that what the picture in your brain is what's actually happening outside. If we're talking about what's happening in the brain, your occipital lobe is actually sending information to your thalamus, and your thalamus is getting information from your eyes as well, and then making sure that everything in the world in your head corresponds to something that's happening in the world around you, in the real world. So, top down processing means you have already have that information in your head, and now you're just making sure your eyes are making sure that whatever you drew is correct. Okay, when you're looking at this picture here, um, your eyes send some information and your brain goes, people don't have yarn heads, they have heads, and then maybe there's some yarn in front of it. And so you're able to sort of figure out what is in this picture because you know what yarn is, you know what people are, you know what heads are. And so your brain figures out what's happening because it already knows what these things are. Now, culture plays an important part of this because if you don't know what something is, well, then you can't figure it out through top down processing, right? Um, Top down processing is important so that you don't have to relearn everything. Imagine if you knew what a chair was, but then you saw a couch and you would go, oh, what is this for? No, you already know what a chair is. And so you just imagine that the couch is a version of a chair. It's just slightly different. But if I change it, right, if I give you something that you don't really know what it is, then all of a sudden it's hard for you to figure out what that is. If you know what a tape is, audio tape is, um, you might know what is relationship is to that pencil. Now, I've had students tell me that the reason um, the the pencil and the tape go together is because you rewind the tape with the pencil. That would take forever. Usually, what happens is that the tape inside will spool out, will kind of come out, and you'll use the pencil to spool it back in. If you've done this, if you're a little bit older and you dealt with tapes on a regular basis, audio tapes, then you just know what that's for. You understand it. But if your only relationship to this is maybe seeing them on the internet, or maybe never seeing them at all, well then you'd never figure that out on your own because there's no top part to this. You don't know what it is because you've never dealt with it. Here's a slightly different one. Let me give you a second to try to imagine what that is. Okay. I've had students tell me that it is an ice bucket or um, just 100 other things. Uh, but it's not an ice bucket. If you don't know what it is, I'm going to give you another clue. It's related to this. Okay. Now, if you don't know what either of these two things are, then you're never going to put them together. But if you are part of the culture that saw it, again, if you're a little bit older, then you might know that it's a flash. Seeing this by itself, you could stare at that forever. It just doesn't look like anything that we have in the modern world. Um, so if you've never seen a flash, or if you've never seen film like this, then you would just never put that together. You need top-down processing to figure that out, and culture is very important for this. Let me show a younger version of this. If you're young, there's a chance that you know what those are. If you're a little bit older, or if you just don't play video games, you may not know what that is at all. Those are just cheat codes. Again, this is a top-down processing. Maybe you've never seen cheat codes like this, but you've seen cheat codes in other places, just slightly different, and you just know that they're cheat codes, even though they look different than the ones you've seen, because you know what cheat codes are. And so you're able to sort of gather this information just by looking at it, even though it's different. Um, Again, this is top-down processing. Now, bottom-up processing occurs when there is no information in your mind associated with what your eyes are seeing. And so you have to put it together piece by piece. And so you look at a blob like this, and you kind of have to figure out what it is. And so sometimes people see a cow here, some people see a person or other things, but this is bottom up. Your eyes start the process, and they send enough information to your brain, and then your brain goes, well, maybe this looks a little bit like that, and that looks a little bit like that, and you go, it's a cow. Okay. Here's another version of this. Here, your eyes have to sort of figure out what to focus on first, and then send that information to the brain, and then your brain can start putting these things together. And maybe at first you see a skull, or maybe you see a person. And then if you look further, if you focus a little bit deeper, you might see a cat or a ship in the background. This is bottom up. uh, you don't know what all of this is together. It takes you a while. Your eyes have to scan it for a while. And then in scanning it, your brain can figure out what is going on. Bottom up processing is why your dog will sometimes bark at a plastic bag for an hour, because your dog's brain can't figure out what that plastic bag is or why it's moving on its own. And so the dog's eyes are seeing something, and the dog's brain is trying to put that together. What could this be? Is it an animal? Is it something else? Is it something that I can eat? Is it something that can hurt me? And so it just keeps on barking and barking at that plastic bag, um, because there's nothing in the dog's brain that will ever say, oh, it's just a plastic bag. It's a human made thing. It just doesn't make sense to a dog. Now, when we talk about perception, we also have to talk about the errors that occur in perception. Now, those errors usually tend to come from a good place, right? Your brain uses those errors to actually make sense of the world just right. But sometimes people can take that perception and mess with it to give you some error. So, for example, uh, a door is always a rectangle. If you open the door, um, it doesn't change the shape of the door. And so your brain knows this. And when you open the door, your brain doesn't perceive the door as being smaller or thinner. You always know the door is a rectangle, even though technically to your eye, the shape has changed. your brain goes, no, it hasn't. It's still a rectangle. And so even though you perceive the door, you sense the door shape change, your brain just perceives it as the angle changing. But of course, sometimes you will look at something like a door, and it'll mess you up. You'll go like, oh, is that a tiny door? And it takes you a second before your brain realizes, no, no, it's just the shape is, the angle is off. Um, the same thing is true with distances. I'll show you a slightly better version of this in a little bit, but distances, usually when someone is further away, you don't perceive that person as being a tiny person. You perceive them as being further away. By the way, this is something that you learn. If you go into parts of the jungle where people are not used to having to look very, very far away, those people don't realize that that thing in the distance is actually a person coming towards you. And so there is some researchers that go into the jungle, and they have documented instances where they go, oh, so and so is coming, and nobody believes them until that person shows up, and then they say, how did you know that? Are you magic? How did you figure that out? And they go, no, look, I can see them from over there. But the people in the jungle culture, um, they they just think like, no, that's just a tiny little bug in the distance or something like that. That doesn't mean that they're dumb. If you explain it to them, after a while, they are able to do it on their own because it's just something you have to learn. But at first, they don't know it, and so they don't perceive it correctly. Um, Color is an issue with this as well. Um, Technically speaking, that white that you're seeing there on the gray background is the same color as the white in the background here. But because you're comparing this white background to the coal and the little bit of gray here, um, you you perceive it as brighter than this white here. You might have noticed every once in a while on the internet, there's a dress that people think is the wrong color, or some shoes that people think are the wrong color. And uh, the issue there is lighting, and what we call color constancy. Because the light in the picture is a little off, and maybe the light where you are looking at the picture might be off, then you will perceive that color as being different. Let me show you a better example of that. When the background is gone, you can see that both of those squares are the same color. They're both brown. But when the picture comes back, the square on the top still looks brown, but the square on the bottom looks like a yellow or a slightly orange color. Now, why does this happen? Well, when you're comparing it to the white background, well, like they're both just brown, and your brain can do that just fine. But when the picture comes back, the brown at the top is around a bunch of brightly colored squares. And your brain says, oh, there's a lot of light there. And this dark brown um, is brown in the light. And so your brain perceives it as brown. But over here, the square in the bottom, all of the squares around that tend to be dimmer. They look dim. And so your brain goes, wait, that the eye is saying that that's brown, but that's just because it's dark, right? Your brain thinks it's dark, even though it's just the illusion of the picture. Your brain thinks it's dark, and so it goes, that's not actually brown. It it's yellow. It only looks brown because it's dim. And so instead of painting it brown in your brain paints it in as a darker yellow. or a darker sort of orange there. Some different people see it. I've had people yell at me because I call it yellow, and they tell me that it in fact is orange, but I see it as yellow. So again, this is an issue with color constancy, and specifically the difference between sensation, what your eyes do, and perception, the way your brain colors in the information. Okay. Another thing you might have noticed is that you see the world in 3 dimensions. That is, you see height and length, but you also see depth. Not all animals do this. Animals like cows, um, deer, don't see the world in 3D. They see the world as a flat image. Specifically, this happens because their eyes are on either sides of their head, and there's no overlap. Their left eye sees the left side of the world in front of them, and their right eye sees the right side. There's a few animals in the world where if you stand right in front of them at just the right distance, they don't see you at all because they actually don't have any overlap. Um, and without overlap, then you can't see the world in 3Ds. Animals that see the world in 3Ds tend to be things like birds, um, other predators, things that jump from branch to branch like monkeys, or that fly, obviously, like birds, have to see the world in 3D. And so their eyes are in the front of their heads, and their eyes have a lot of overlap. Now, here is a little bit of a visual. Um, your left eye, if you're looking out into the world, your left eye can see everything on the left, and your right eye can see everything on the right. But there are parts of the visual field in your left eye that your right eye cannot see, and vice versa. There's a portion of your visual field that your left eye can't see, even though your right eye can see it. Not only that, but your brain takes into account the closeness. So your left eye, if you look at the tree there in the distance in the left, um, to your left eye, that's very close. And so it looks a little bit bigger. And to your right eye, that those women look a little bit bigger. And you can see that there is a difference, not only in what your left eye can see, but how big it is versus your right eye. And yet there is that overlap that that both of your eyes can see. And so your brain takes both of those images and puts them together to create a 3D picture, a 3D picture that includes height and length, but also depth. Um, Now, when you go to a movie and you see a 3D movie, there is no depth. It is all a trick. And the way the trick is done is that uh, 3 images are superimposed onto uh, the screen, but your lenses, your 3D glasses, only allow you to see a certain amount of that. And so your left eye can only see the red and the actual image, the normal image. And your right eye can only see the blue and the actual image. And so 2 separate images are being sent to the brain. And your brain goes, oh, that must mean that there's a difference in what my left eye is seeing and my right eye is seeing. And so therefore there must be depth. Uh, and so now you can see a 3D image, maybe a ball coming towards you, when in fact there is no ball coming towards you. Your brain has painted an image inside your mind that does not exist in the real world. Um, Now, if you are looking at the 3D world, then uh, the depth is real. Now, not every human can see the world in 3D. If you are born with sight to only one eye, then you cannot see the world in 3D. You see the world as flat. We know this for a fact because sometimes someone born with vision to only one eye can have that corrected. And as they get older, right, they go to surgery and now they can see with both eyes. And what these people report is that the world looks like it's popping out at them, right? Because before, everything looked like a TV. It looked like, if someone was in front of you and they put out their arm in front of you, it didn't look like they were closer to you. It just looked uh, like a TV, flat. Um, but now, with vision in both eyes, everything looks like it's jumping out at them because now they can tell that somebody's hand is closer to them than the rest of their body, of that person's body. Now, whenever I say that, people start closing one eye or the other. And you'll notice that if you close one eye or the other, the world doesn't turn flat. That's because once you've learned that the world is in 3D, your brain will try to keep a 3D vision even when it's not getting the information from the second eye. If someone loses one of their eyes, it will affect their depth perception, but it won't turn the world flat in front of them. Um, Why? Well, because your eye will take what we call monocular cues. It will try to maintain the 3D perception from simple things that one eye can provide. So, for example, interposition. If one thing seems to be in front of the other, well, then I can assume that that thing in front is closer to me and I can draw it as closer. Um, Height of proportion, if I see that something in the distance looks smaller, then again, I can imagine that that's further away. If I know that a person isn't going to be this 2 inches tall, then my brain goes, well, that person isn't 2 inches tall, that person is just further away, and it will draw the depth in order to keep the 3D image going. Okay. Another thing that your brain will try to create or to try to perceive is a difference between the figure and the foreground, or I should say the background. Um, so, in anything you look at, you will automatically focus on something that is the image and then whatever is in the background. And depending on what you decide is the image, you might see it here, maybe a man with a mustache, but if you decide that all of this is the background, then you might just see a woman with a veil on top of it. Um, it just depends on what you decide is the foreground and the background. Um, Another thing your brain will do is that it does closure. If I ask you what's here, 95% of people are going to tell me that it's a triangle, even though it's not. There's clearly a missing part. That's because our brain will naturally close it up. It'll say, yeah, that just looks like a triangle. Yeah, it's missing a part, but it just looks like a triangle. Because we close things up to make it easier to understand. This is super important in the brain. It's why if you see a broken pencil, you still know that it's a pencil because you see one part and your brain draws in the rest. Um, and it's an important way of how we find patterns in the world around us. But sometimes, if you break it just right, it'll sort of mess us up. Another thing we all do is that we all group things by distance and similarity. If I tell you how many groups are here, or ask you how many groups are here, most people are going to tell me that there's 4 groups, and very few people are going to tell me that there are 6 groups, right? 1 line, 2 line, 3 lines, 4, 5, 6 lines. Some people might tell me that there are 12 groups, so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 short lines. But most people are going to see that as four groups of 3 lines. Why? Because the distance between this group and this group is large enough that we go, yeah, these guys are not together. And the distance between this group and that group are large enough so that we tend to say those things are not together. We group things by distance. We also group them by similarity. If I ask you to group these, most people are going to tell me that there's 3 groups of clover and 2 groups of diamonds. And if I ask you, are there lines or columns? Most people are going to tell me that there are lines. Because hardly anyone is going to tell me that there are columns of clover, clover, diamond, diamond, clover, clover, diamond, diamond, clover, clover. Even though, yeah, technically speaking, that is a column like that. But most of us group by similarity. And so it's easier to say that there are 2 rows of clovers and then 2 rows of diamonds. 2 rows of clover and then 2 rows of diamond. That's just easier, and most of us will group things that way. By the way, film uh, directors and producers take advantage of this. Every once in a while, they'll introduce a couple, let's say, and they don't have time to go into background. And so what they'll do is that they'll make that couple wear a similar color. He'll be wearing a blue shirt and she'll be wearing, I don't know, a blue bonnet. And you know what happens? We put those people together. Even though the storyline never says that they're a couple, we just assume it because they're close together and they are both wearing a similar color. And so this is a very quick shorthand that directors and writers use to sort of put people together, even though they're not together. Even though there's nothing for us to make us assume that otherwise. Now, some errors will occur because of this. Every once in a while, you look up at this moon and you'll say, wow, the moon is so big. And then you'll take a picture of that moon and that moon will look tiny, tiny, right? And you go, wait, how come my phone is so awful? It doesn't actually make the moon look bigger. That's because the moon isn't bigger. Only your brain paints the moon as bigger. When your brain can compare the moon to whatever is in the horizon, some um, excuse me, some buildings, for example, well, then the moon looks enormous. But if the moon is up in the sky high, and the only thing you have to compare to the moon are the stars and the enormous sky, well, then the moon looks tiny. But if you were to measure the moon in the sky and measure the moon in the horizon, you'd realize that the moon always is the same size. It's never actually bigger. This is completely a error in your brain. By the way, you might ask yourself, wait, the moon in that picture is clearly bigger. This is also a trick of the camera. These cameras are, their lenses are opened and left open longer, and that will allow more light to come into the lens, and it will give the moon a larger appearance. Okay. Sometimes you're driving down the road and you see this enormous light, traffic light, except it doesn't look enormous. It looks like it's tiny. It looks like it's like an inch big. And we know that it's not an inch big, but we never assume that it's this large, right? That it's almost half the body size of this woman, um, or well, more than half the body size of that woman. Um, I think most of these are tend to be like around 3 to 4 feet in height. It just don't look that big until we can have something real to compare it to. This little Tonka truck might look very tiny until you compare it to that school bus behind it. And then you realize that, in fact, it's enormous. Here's something else you see on a regular basis that looks big, but not this big. If you see the man working on this road sign, now you see that the road sign is enormous. Um, where when you're driving down the road, it just looks like it's a sign that you would make, I don't know, out of paper. It just doesn't look that much bigger. Here's a common uh, visual error. If you look at these two lines, just the lines, not the arrows, it looks like the line on the right is much larger. But if I were to actually measure them, here it is, and then I measure the other one, I realize that they're both the same size. But if I take this away, oops, it doesn't, you didn't learn anything by measuring it. Your brain still sees the line on the right as longer. Again, this is just a visual misconception that occurs all the time. Here's another one. If you look at this picture, the thing in the back running, the man running in the back, looks bigger than the man running in the front. This is the same issue with the moon. If I were to take away the background and then measure them, I would see that they are in fact the same size. But if I go back, it's like your brain didn't learn anything. The thing in the back looks bigger. That's because your brain is comparing the man in the back to the environment, which is a what looks to be a hallway getting smaller because of distance. And so your brain goes, no, that guy has to be really big. Look at how big it is compared to the tunnel. And this guy, compared to the tunnel, is really, really small. But of course, that's all a visual illusion. Again, when you put them together, they are all the same size. Okay, guys, you're going to read a little bit about some of the stuff that I talked about, and a little bit more as you read through the chapter. Um, uh, Again, if you have any questions, please let me know. Um, and remember to finish your mind taps this week for chapter 3. All right. Have a good one, everyone.